Okay, so continuing our discussion of sequences and series, in this case we're focusing on geometric sequences and series. So yesterday the focus was arithmetic, in other words, ones that had a common difference between each successive term in the sequence. You're adding a certain amount, subtracting a certain amount. With geometric series and sequences, you're multiplying each successive term by a common ratio. So a sequence in which successive terms share a common ratio is the definition for geometric sequence. So take a second and note that definition. Successive terms share a common ratio, which is usually R, the variable R. And then here you have the nth term formula. So you remember the formula for the nth term of an arithmetic sequence from our last lesson, 10 part 2. Here's the nth term for a geometric sequence. And it's a sub n equals a sub 1 times r to the n minus 1 power. A sub 1 is, of course, always the first term. And then r is that common ratio. Now the sum up to term n is, there's a couple different scenarios. Scenario 1 is this finite sum formula. And that's 1 minus r to the n power over 1 minus r inside the parentheses there. And then there's also this formula, a sub 1 minus a sub n times r over 1 minus r. So just like arithmetic sequences, there's two formulas. I'll probably use the first one primarily, but the other one exists if you need it. And then lastly, if we want to have an infinite sum, so we want to sum up an infinite amount of terms, the sequence has to be convergent. So this only functions if you have a convergent sequence. In other words, one that approaches a constant value. So if it is convergent, its infinite sum is given by this expression, a sub 1 over 1 minus r. And you might be curious, how could the sum of an infinite number of terms be anything other than infinity? Well, it can. It's difficult to wrap your head around, but it can. Take, let's say a sub 1 equals 1/2, and the common ratio is 1/2. First term is 1/2, second term is 1/4, third term is 1/8, and so on. So what if I started adding those together? With this, I mean, I'm adding a little bit more each time. Surely it would. And if I just keep doing it. am I getting closer and closer to?
1.
Yeah, if you add up all the infinite terms of that, you get to 1. So it is possible to have an infinite summation that is just a single constant value. It's curious, and again, kind of hard to wrap your head around, but it is possible. Okay, so pretty famous proof here. If I start adding up all the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to infinity, you would think the only possible result is infinity. But strangely, using something called Ramanujan mathematics, you get this result, -1/12. This has been called the most mysterious result in all of modern mathematics. And a lot of modern mathematicians just scoff at it and say, it's not true. I can't prove that it's not true, but I don't believe it. So it's almost dogmatic the way people treat this. But here's a really fascinating fact. This is used empirically. In other words, in physical experiments done in quantum theory. So there are things in the real world that confirm this result. Really strange. But if you're interested, Numberphile on YouTube has a really cool video on it where they do the whole proof. I won't bother you with it here. But the Numberphile video on this is really cool. Okay, so let's find the next 3 terms of these geometric sequences. So to find R, I will take any term and divide it by the term that came before. So R in this case is -1/4. And to find the next 3 terms, I'll just multiply 1/2 times -1/4 to get -1/8, and then again to get +1/32, and then again to get -1/128. So to get the common ratio, take any term and divide it by what came before, the previous term. Of course, you can't choose the first term for this because there is no previous term for the first term. So choose any term after the first term and divide it by the previous term. Let's look at part B here. So R equals 2W plus 6 over W plus 3. What do you think that would reduce to, Jesse?
W plus 2.
Not quite. Do you see how there's a greatest common factor in the numerator? Yeah, there's a GCF between these 2 terms in the numerator.
Oh, yeah.
So I can factor out a 2. Bet you can figure it out now. What would that reduce to?
2.
Just 2. So my common ratio is 2. Finding the next 3 terms, or 3 terms, right? I just multiply by 2. So that's 8W plus 24, 16W plus 48, and 32W plus 96. So the common ratio in this case equals 2. And sequence terms don't have to be real numbers. They can be algebraic expressions like this. Might be the first time I've thrown something like that at you. But it is an option. Any of you guys eating lunch, by the way? Supposed to ask. Nobody? You are? Okay.
I'm sure, probably. I think so. It depends on what it is.
Okay. So I'll just send in 2. My A cohort, they always have 0, so I kind of get out of the habit of asking. Tony Williams. Suppose I should. Have a title. All right. So here's one for you guys. Find R in the next three terms for these two sequences. And feel free to raise your hand if you're unsure how to proceed. You may want to use your calculator for that first one. Some fractional mathematics, which sometimes is challenging to do mentally. Do you hear, bro? Something Eagles? Something Eagles?
Yeah.
Probably chopped a box of food or something. That's a pretty deep cut, not to notice, bro. You must be like a stoic person. Although I once got stabbed and didn't know it. That's true. That's illustration. Got stabbed in the bicep, didn't realize it until afterwards. And only then when somebody was like, hey dude, what's wrong with your arm? I was like, oh crap.
Okay, I don't know if I'm doing this wrong.
There's a stab wound.
This is correct. So now you're gonna times this by this to get here.
Yeah, but I got that.
Yep, that looks about right.
Okay, so do I just round to the 10th or you want me to follow?
Yeah, let's just go to the nearest, well,
Or well, 100.
yeah, nearest hundredth should be good, so 83.19. You don't wanna have to write 20 digits there. Which could potentially make your answers vary just a little tiny bit, and if they do, that's okay.
Should we just round to like the nearest tenths place?
Hundreds, I think.
Hundreds in there.
Yeah, hundreds, I think. Let me know if you're confused again. Part B can be a little tricky. Use the same trick I did. Good job, buddy. Another few seconds here. Right. Oh, what's the R for part A? Good. Or 2.75, I think. Ian, what comes next here?
82.5.
That's to the nearest tenth, I guess.
That's on it.
Yeah,
I got 83.19.
Yeah, that's what I was
Yeah,
thinking.
that's my bad.
So I'm not sure you punched that in your calculator right. It would be a shame to miss one for that reason, so be careful with your calculator inputs. Rowdy, what comes next, buddy?
I got 228.77.
And then what's last, Jesse?
69.1.
Say again?
629.1.
Thank you. All right, those are approximate because the real decimal has 16 places, I think, by the end, so, which are mathematically artifactual. Significant digits and all that. Tell me what the common ratio is for part B, Rachel.
Negative 0.2.
Good, or negative 1/4 if you prefer. So either of those are accurate. And if we look at what would come next, the sign on the R term is going to change every time. And then the sign on the constant term is going to change every time. And it's going to reduce by a factor of 4. So we're going to divide it by 4. So the next one would be positive R over 4 plus 1/2. 2 divided by 4 is 1/2. And then the last one, negative R over 16 plus negative, what minus here?
The negative should be on a 1/2.
Yeah, that's my bad. Thank you. And then this is a positive. Yeah, okay. So every term, those signs change. Let's see, so that is 8, yeah. So that can be kind of tricky on that. Questions about this? Geometric sequences. Super fun. So explicit and recursive formulas. Let's write some formulas. First of all, the explicit formula, we're going to use the nth term, just like we did with arithmetic sequences. And remember, it looked like this. A sub n equals a sub 1 times r to the n minus 1 power. So if I've got a sub 1 equals 8, so that's 8 times the r value, which is negative 0.25, to the n minus 1 power. So this is the explicit formula. And now a recursive formula for this. So I'm going to say f sub 1 equals 8, and then f sub n equals f sub n minus 1 times negative 0.25, and that's for n greater than or equal to 1. No, 2. So the second and subsequent term. There we go. Okay, any questions about explicit or recursive formulas? All right. In that case, here's one for you. Give me the explicit and the recursive formula. Don't quite feel myself till I have a second cup of coffee. Man, we're drug out of the world now. You get to see where Virginia is proposing recreational marijuana legalization.
Yeah, that's not good.
It'll be quite a thing if it goes through. It's going to, of course, have effects here because we're 20 minutes from the Virginia border. Bristol's going to have a major casino. So, yeah. We're turning into a different area. Give me just another second here. Okay. Roddy, can you tell me what the explicit formula would be?
It would be 4 times -2 to the n minus 1.
Very good. Now, when you raise a negative power or negative base to a power, make sure you put it in parentheses. And in your calculator too. Because let me just demonstrate. If I want to -2 to the 4th power, for example, and I just do this, gives me -16, but that's not right. Because -2 times -2, +4, times -2 is -8, times -2 is +16. So you have to put this in parentheses, or it will give you the wrong sign sometimes. So be careful with that. Common problem. What is my recursive formula, Ian?
As to n minus 3rd and it'd be f
Good.
and f of n equals f n minus 1 times -2.
Very good. A little subtle difference in your notation. It's not f of n, it's f sub n. And sometimes I say that so quickly you might have difficulty distinguishing between the two, but f sub n. F of n is this. So that's different. It's a function of n. This is just like a last name for the variable. F sub n. Yes, ma'am.
So is that always going to be n is greater than 2?
Yeah. Because you have as long as it's only the first term defined. That's a little bit different in the Fibonacci sequence, for example. So this is just an aside. This has nothing to do with this particular problem. This is to address Rachel's question. So with the Fibonacci sequence, I get this. So the first 2 terms are defined, and this expression holds over the 3rd and subsequent term. So usually, yes, there are a couple weird exceptions. For geometric terms, or geometric sequences, yeah. Just weird ones like Fibonacci, you'd have something else. All right. Find the 27th term for this. So, and there's a shortcut, so if you're not, you don't have to find all the intervening terms. You need only find the single 27th term using the Nth Term Formula. I'll show you how to do it. So 189.151.2 and 120.96. Need to find my R value. So R again is choose any term other than the first one. Divide it by the previous term. So that's my R value. And that probably simplifies. Let's punch it in the calculator and see. 4/5. Wow. Would not have guessed that, but that's pretty cool. All right, so A sub n equals, and remember it is A sub 1. I'll just write the formula out first. Help you guys remember it. So there's our nth term formula for this particular sequence, and we're interested in n equals 27. So A sub 27, the 27th term. And as I told the A cohort on Tuesday, I started picking bigger and bigger numbers for this because I had kids that would brute force it on quizzes and tests. In other words, they would write out. If I said 17th term, they would write out 17 terms, just so they didn't have to do this. So I started picking bigger and bigger values, 65, stuff like that on quizzes and tests, just so you have no option other than this. Okay, 189 times 4 divided by 5 to the 27 minus 1 is 26 pounds. So 0.57, does that change into a fraction? Nope. So about 0.57. It's interesting that it would actually be a fraction. It would just, the TI software couldn't store enough digits in memory to remember what its original fractional formulation was. It had to truncate so that it didn't overflow the RAM. And when it truncated or cut part of it off, it no longer reduced. Pretty old, crappy piece of software, isn't it? But it's worth, what, 120 bucks? Oh, interesting. It's almost like they cornered the market for an important test and made sure their calculator was the only one that could be used on it. Okay, so find the 27th term for this one for me. I'll give you a couple minutes to work on that. Yeah, big boy. These geometric terms grow very rapidly. So scientific notation is fine for that. 2 digits times 10 to the whatever power. Yeah, big boys. So remember the last one, the decimals were too long for the calculator to remember. Here they're too big.
2 minutes.
Too big. So that's one of the reasons why it's disadvantageous to pick these big terms, because geometric sequences, unless your common ratio is really close to 1, is going to quickly diverge towards positive infinity or negative infinity. If it's less than 1, of course, it would approach 0. Get a lot of decimal values real quick, or a lot of other values real quick. Holden, tell me what A sub 27 is here.
5.6 times
Good. So So just out of curiosity, let's see, 1, 2, 3, 1, 2, 3, 2, 3. So that's 9, 10, 11, 12. And then 2 more spaces. So let's see. There we go. That's an approximation. And let's see.
Right.
Millions, billions, trillions, 560 trillion.
I think I may have done something.
Let's see what we got.
It's just like the same equation as this, right?
That's pocket change.
So I did 14 plus 7 2.
Which is correct.
I saw that.
And 4 times 4 2. 1.
You know, check business.
And
You see, you know, this is wrong.
then, oh,
Yeah, that E to that E14 at the end means this.
okay.
It's the same thing as this. So you actually had it in there. All right, good
Oh,
question.
it's the-
It's just the way your calculator says it. Because they don't want to use those extra characters if they don't have to. Other questions? All right. Example 5. We skipped 4 again because it's a pretty obscure thing that doesn't get used very much. So we're going to use geometric means. And you'll remember from Tuesday's video, we did arithmetic means. Geometric means work very similarly. And here we want to find 2 geometric means. We can pick as many as we like between 2 values. But I know this would be my a sub 1, and this would be my a sub 4 because of 2, 3, 4. It's the 4th term. If I had a different number of blanks here, this would be a different subscript. So let's write I need to find R is what I need to find. So I know a sub n equals a sub 1 times r to the n minus 1 power. So in other words, a sub 4 equals 480 times r to the n minus 1 power. And I also know that a sub 4 equals negative 7.5. So I can set these 2 values equal, and n minus 1 in this case is 4 minus 1 or 3. So I should put that one. So this expression is equal to negative 7.5, meaning I can create an equation, spoiler alert, can create an equation like this. So if I divide both sides by 480, get this, and then take the cube root of each side. I get this, so let's see what that looks like. You remember one way to take the cube root is to take it to the 1/3 power. So let's do that. Looks right. Negative 1/4. So there's my R value, meaning I can now go back to the original problem. And multiply this term, 480. The quick way to do this in your calculator, times negative 0.25. And then I could just do times negative 0.25. So negative 120 and 30. Those are the geometric means. A little more complicated than the other things we've done, but within your power. If you guys can beat the boss in a Dark Souls game, you can do this. Demon Souls coming out for PlayStation 5. That'll be dope.
Can't wait.
Most of you guys don't even know what that is. It was the most obscure from that gaming series. PlayStation 3 game, early PlayStation 3, like when PlayStation 3 was brand new, I think it came out. The first FromSoft game in the Souls series. Here's one for you. Tell me what the geometric means are between two geometric means between 10 and 402. Give you another few seconds here, guys.
What if you multiply the third term by R and you get like 403?
That's okay.
Okay.
That's a consequence, Jesse, of rounding,
Yeah.
because there were so many decimals. So you rounded at a place that made that just a little bit off at the end, which is okay. Totally good. All right, Jesse, tell me what the first one is here.
You know, the second term. 34.3.
Good. Then Colin, what's the last one here?
117.
Yeah, I had 0.6, but depending on how you rounded, it might be a little different. Because it was 0.649, so it was 1,000th away from rounding up to 0.7. Excuse me.
What was the R for that one?
So the R was about 34.3 or 3.43, sorry. About 3.43.
Yeah, I think I did. So I got 6 point.
Oh, I just put the exact right.
This is right. Let's see how you did it. Okay. Yeah, you used the square root.
I don't get 3. That's right.
Other questions? Yeah, square root and cube root are not interchangeable. Different mathematical entities. So let's do some sums. These are some series of geometric sequences. We're going to sum the first 6 terms. And, you know, I picked only 6 terms here, meaning we don't necessarily have to use the formula. We can brute force it, but we won't. We're going to use the formula. So a sub 1 equals 8. R equals 14 divided by 8, which is 7 over 4. So I now have a sub 1, R, and n. So I need those 3 things. N is 6 in this case because we're told to sum the first 6 problems. So this tells me the first 6 terms. It tells me that n equals 6. So plugging that into our formula.
Couldn't use that summation thing, calculator?
Yes, which we will on the next example. You can use your calculator for this. So 8 times 1 minus 7 over 4, and then the n is 6. The 6th power over 1 minus 7 over 4. Now this is going to be complicated to put in the calculator. A lot of potential for error here. Watch how I use my parentheses. Okay, so this whole thing is the numerator there. So it's 8 times 1 minus 7 over 4 to the 6th, and then divided by, and we're going to put in the denominator, which is 1 minus 7 over 4. I believe that's right. 295.72 or 71, yeah. Go approximate here.
Could you scroll up a little bit?
Yeah, that's correct. A lot of potential for calculator error in that problem. So to find a geometric series, you need a sub 1, you need r, and you need n. A sub 1, r, and n. Questions, anybody? All right, cool. Here's one for you. Sum the first 10 terms for this sequence. You got a negative r, make sure and put that in parentheses. Yeah, this should be, remember in the formula, minus. But the tricky part here is negative is the ratio.
Oh, no, I'm multiplying. Okay.
So it works out like that.
Okay, gotcha.
You really have to be careful. This product,
Is it 1 minus 2?
I just did one plus two.
Yes.
that's right. All right, Rachel, tell me what S sub 10 is in this case.
Is 7, wait, hold on, the full answer?
Mhm.
Okay. Negative 2,387.
Excellent. So, make sure you, again, are careful with your calculator inputs. So much potential for error when you have to put these complicated expressions in. And parse it for plausibility, you know. Do you see how the even terms are negative and they're always going to be greater than everything that came before? So every even series is going to be negative. Every odd one here is going to be positive. So if you got this as a positive answer, you would know, wait a minute, something's wrong.
The 28 on
Yes, that's the third term. So the odd ones are positive. And it's bigger than all these
I
put
thought you were
together.
talking about the actual value of the numbers. No.
The sum, if you added them all up. Yeah, if you added them all up, this would be
I got you.
positive, negative, and so on. Okay, so let's do a sigma summation. Remember, we need three things to do this with the formula. We need n, we need a sub 1, and we need r. So finding those from this formulation can be a little bit challenging. N is going to be upper bound minus lower bound plus 1. So that's 7 minus 2 plus 1 or 6. A sub 1, we need to plug in that first term. So that's 3 times 5 to the 2 minus 1. We plug in whatever this first value is here for n to get this. So 2 minus 1 is 1, so that's 3 times 5 or 15. So we've got n, we've got a sub 1. And now we need r, and we see that in this formulation, the common ratio is 5. So we plug that in for r. Now we can use our formula. So S sub 6 is going to be the a sub 1 times 1 minus r to the 6th power over 1 minus r. And if it helps you with the calculator bit, you can do these, the numerator and denominator separately. So negative 15624. That would be a good way to check yourself. 3906. File 0.08590. Of course, a really easy way to check your answers here is to use the summation function on the calculator and just plug in those values. Assuming you have a recent enough one to include that summation, which I believe we all did. Excuse me. So let me put this on the old camera here. So this was, it's not really helping, is it? From x equals 2 to 7 of 3 times 5 to the x minus 1. And now we get a confirmation of our answer. All right. Questions about anything we've talked about? How you guys feeling about sequences and series? We just spent 3 days on it, so
Not too bad.
I feel like we've
In all
covered it.
honesty, it seems like the easiest
Yeah.
out of everything that we've done. For me, at least.
Yeah, patterns are really the bread and butter of a mathematical mind, the human mind in general. In fact, we're so adept at seeing patterns. There are examples in history of people seeing patterns where none exist, like constellations. Ancient humans would look up there and see bears, lions, and so on. Of course, there was no such thing. Just a random formulation of dots in the sky. But they'd superimpose some pattern over it because they were so adept at seeing patterns. They even saw them when they weren't there. Pareidophobia, I think, is the name for people that love patterns so much they see them where they don't exist. Kind of like if you look at voting results, and you really want a certain thing to be true, and you see a certain pattern of votes, maybe that's a little mysterious. That's also called confirmation bias, by the way. So one more. We'll talk about the sum of an infinite series. So with a geometric series, if the common ratio is greater than 1, it is automatically divergent. If the common ratio has an absolute value between 0 and 1, it is automatically convergent. So absolute value greater than 1, divergent. Absolute value between 0 and 1, convergent. So the common ratio must be between 0 and 1 for its absolute value for the infinite sum to exist. So let's see. How about this one? 9 plus 3 plus 1. So if I wanted the infinite series here, the formula, as you recall, is a sub 1 divided by 1 minus r. And it's only true for the convergent series. So the sum of the entire series is going to be a sub 1 over 1 minus r. So here I see the ratio is 3 divided by 9, which is 1/3. That is between 0 and 1 for its absolute value. So it's convergent. All right, and we'll plug it into this formula. So the sum, if I were to add these up forever, it's going to be 9 divided by 1 minus 1/3. So that's 9 divided by 2/3. Remember how to divide by a fraction. Keep, change, flip. So I keep, change, flip here, and this is 9 times 3 over 2. 27 over 2. 13.5. So if I added these up forever, and that's interesting because you see 9 plus 3 is 12, plus 1 is, we got 13 right here. Everything else forever is 0.5. Wow, man.
Well,
Yeah.
Geometric series are pretty interesting in that respect. Okay, so a brief little assignment for you guys. You got a half hour left here, so plenty of time for you to work on it. Sure, bud. When he returns, the next person may go. All right, let's see here. That's what I'm looking for.
All. And chapter.
Yeah, this is mine. Pretty.
All right.
I'm done with that one.
Yeah.